This is my second welcome to the third annual PARLAB Bootcamp. We were looking at our history, and it was 6 years ago now that a bunch of us, including Jim and many of the people on the stage, got together to start talking about parallelism. We spent 2 years talking about what the implications were and wrote a technical report, the Berkeley View of the Parallel Computing Landscape, which is a very long technical report, but yet widely cited. That led to us winning a competition that Intel and Microsoft sponsored to set up $2 million a year for 5 years, which we just went through the mid-project approval. Those two founding companies have been joined by 6 others. 4 of them start with N. Let's see, National Instruments, NEC, Nokia, NVIDIA, and then Oracle and Samsung. We started off being driven by applications. That was the idea of this thing, is rather coming in like a lot of parallel projects that we knew what the answer was, and the goal of this project was to prove that was the right answer. We started off with lots of ideas, but no bets in advance which ones were the right answers, and we let the applications drive that. 3 years into it, we've got a lot of exciting technologies, which you'll hear about today. We are doing this, none of the people up here are getting paid. This is all done out of the goodness of their hearts. We did this originally for the incoming graduate students, and then as people found out about it, more people wanted to come besides the graduate students, as well as people coming in electronically, so welcome to you out there in the ether. This will be, even architecture, which I'm supposed to know a lot about, I found it's really great to force the faculty to give you encapsulate everything in 2 hours of everything that's going on in the field. So I'm sure I'll learn a lot. With that, I'll turn it over to Jim. Demmel, within the last year that you've seen him, he was before the high honor of a member of the National Academy of Engineering, I think in part because of the work in the PARLAB, but for his whole career, he was elected to the National Academy of Sciences as well, which is a great honor. Here you go, Jim.
So, welcome. I hope everybody out there can hear me as well. So, Dave gave a great introduction, and I'm going to spend the next half hour telling you more about the motivation, the pedagogical basis of how we're going to teach, which follows out of the research of the PARLAB, and then the logistics. And this worked when I tried it just a little while ago. Interesting how it changes. All right. So, here is all right. This worked perfectly well just a little while ago. Why is that? Let's try again. Okay. I'll start with the motivation and goals. I assume you're all well motivated because you're here in the first place. Then I'll tell you about the background. You already heard a little bit about the PARLAB, which is this research center. And as I said, it's motivated a lot about the way we teach this material. For the folks at Berkeley, we also have started a new graduate program recently. In Berkeley Speak, a designated emphasis is a graduate minor. So we teach a lot of other courses besides this one in parallel computing, and I'll give you a little overview of that. There are a lot of other resources for people who are here. For example, there's a lot of computational science and engineering that goes on at the neighboring DOE National Lab, Lawrence Berkeley National Lab. They run one of the world's largest supercomputers, and they have a big intellectual apparatus of brilliant people with whom we collaborate. They're also a local resource. And finally, Exceed is the new NSF project, follow on to the TerraGrid. It was just announced, and they are broadcasting a number of Berkeley courses, including this one, across the nation because they've decided that's the best way to teach people parallel computing. So I'll give you a little background, tell you about the schedule and the instructors, the logistics. Coffee is important, of course. I'll tell you all about the coffee. And then a little bit about yourselves, some statistics from the people who've signed up. So as Dave said, parallel computing has become ubiquitous. The only people who don't care about it are the ones who are perfectly happy with how fast their sequential laptops ran back in 2008 because sequential speedup basically stopped back then because of technological trends. Unfortunately, parallel programming is still a lot harder than sequential programming, even though there are a lot of research projects like ours that are trying to build better tools. So in the meantime, we're going to tell you about those new tools that are coming along, but also teach you sort of the basic tools that are available now that you can go home and use to do parallel computing. So, welcome. I've mentioned these already. There's the PARLAB. I'm going to tell you about that in a little bit more detail. I'm going to tell you about the designated emphasis. When we first asked whether people on campus were interested in training their graduate students in computational science and engineering, I sent out a few emails to my colleagues in mechanical engineering and astronomy with whom I'd collaborated before. And by the time it was over, we had 117 faculty from 22 departments who said, we need to train our students in this stuff. So I'll give you a little overview of how that's led to a new curriculum. And then, again, Exceed, the new NSF follow-on to the Terra Grid. So what are we going to do? We're going to teach you the basics about parallelism. There's going to be hands-on labs. In fact, there's a number of them. You're going to get to choose depending on which framework you want to learn. And you'll have time to do more than one if you like. Tools that you can use now, both simple and advanced. So it's not just programming languages you have to know. There's a lot of other pre-built stuff, including debuggers, debuggers for correctness, debuggers for performance that you're going to hear about, and then tools that we're in the process of building and future research. So the PARLAB in the background here. So as Dave mentioned, our starting point, and this was a number of years ago, was an observation made by a colleague, Phil Colella, at Lawrence Berkeley National Lab, who looked at all the high-performance computing applications that they do on their supercomputers to figure out what were they built out of. And he observed that there are only 7 kernels. There are only 7 things that are done over and over again. And if you could simply implement these in an easy-to-use and scalable and composable way, you could basically do all of high-performance computing. So what were those 7 kernels, which he called the 7 dwarfs, because there were 7 of them? There are operations on structured grids. Basically, you have data points on an array, and you do some operation each point averaging them with their nearest neighbors. There's operations on dense matrices, linear algebra, solving linear systems. There's operations on sparse matrices, same idea, except the matrices have mostly zeros inside of them. Spectral methods, variations on the fast Fourier transform and other things. Particle methods, pushing particles around because they depend on faraway forces like gravity or electrostatics. Unstructured grids, which is similar. You're connected to some neighbors, but every point has different neighbors. And again, you update yourself depending on your neighbors' values. And then Monte Carlo, lots of embarrassing parallelism, people doing stuff. So that was our starting point. We figured, OK, that's good enough for high-performance computing. But if the whole computing industry is going to change, we have to ask ourselves, is that enough? So besides HPC, high-performance computing, we looked in this group of faculty and students that Dave referred to. We looked at computer-aided design, machine learning, games, databases, the spec benchmarks, and embedded computing, and we asked, well, what are they built out of? And we came to the conclusion, to our surprise, that all these 7 dwarfs appeared, and only 6 more. So now there are a total of 13. And in fact, there are 13 dwarfs in The Hobbit by Tolkien, but we decided to change the name, because there's nothing sort of sacred about 7 or 13, so they're called Motifs now. And there are only 6 more that appeared over and over again, and this heat chart tells you how much each component appeared in which application area. So there's finite state machines where you get a sequence of inputs and change state depending on some rules to go to the next state. Circuits are evaluating large Boolean expressions. That happens all over the place. Graph algorithms, traversing graphs, breadth first search, depth first search, performing sort of updates at each node that you come to. Dynamic programming, which is a familiar, you're updating an optimum based on some previously solved problems. Backtracking and branch and bound search, searching trees for optimal solutions of things. Graphical models is kind of a catch-all for lots of AI techniques, hidden Markov models, things like that. And then and the other 7 appeared too. So you can see that they're all used throughout these other commercial applications, not just high-performance computing. So being that I'm a dense matrix guy, I was pleased to see that dense matrices appeared everywhere, so lots of applications for that. So then when we formed the PARLAB, what we did was we said, OK, we're going to pick a few driving applications, and we picked them from health, image processing for stroke victims. We picked them from image analysis, find me all the pictures that have my sister in it, no matter how she's posed. Speech recognition, so you could have your laptop take notes no matter how fast I speak. It would give you a transcript of what I said. Music applications, you can make your living room sound like Carnegie Hall, row 4. That takes quite a bit of processing. And then making browsers run faster. So those are the driving applications. They all use all of these different motifs. And in the very last lecture of the short course, you will hear how we have architected those applications using all the tools you learned about in the previous parts of the short course. Now, what happened to Monte Carlo? So it disappeared from this list. That was the 13th one. So it turns out that in our looking for patterns or motifs, in order to decompose your applications, we decided that you didn't just need these computational ones, you needed a few more layers. And so you're not intended to read this whole slide. There'll be a whole lecture on it later. But those 12 computational patterns appear over there. Those are where your code is going to spend most of its time. Hopefully it's already been done for you, right? You recognize that you need this pattern, somebody has solved it, but you need to compose them in certain ways. And the other patterns up here are how you compose these different, more basic, simple computations. So, for example, Monte Carlo has been renamed MapReduce, a more popular name. It's the same idea, right? You do a bunch of embarrassingly parallel stuff, and then you combine it. So all of these other ones, which you'll hear about in more detail later, are how you compose the high-level computational patterns in a certain relatively small set of ways, so the whole thing can be parallelized. So if you're only interested in writing a program and having it run fast and having somebody else do all the work, you're called what we call a productivity programmer. You know, and all of these patterns are the things that you have to know to get your program to run fast. If you're a computer science hacker kind of person and you want to build this stuff and make it run as fast as possible, there are a bunch of other patterns which lie underneath it, below this dotted line, and those are things that a bunch of us do research on, and you'll hear about those too. So depending on your point of view, you may be interested in these patterns or those patterns or both. Okay, so let me tell you a little bit more. And so that is the basis, these patterns here, let me go back, is the basis of how we teach the stuff, how we teach people to think about parallel computing, and it's why I think, you know, NSF thought this is a good idea. This is how we want to teach everybody in the country. So let me tell you about the designated emphasis. I already mentioned we have lots and lots of faculty from many different departments. I'll just give you a few slides on how it works and what resources there are, because we have more resources that you'll want to use possibly after you leave this short course. And there's a website with lots and lots more details. So it's a new minor. So the way it works is that you get admitted to your graduate program at Berkeley, whatever it is, one of these 22 departments. And when you get here, you decide, oh, I need to learn how to do high-performance computing or analyze large data sets. So then there's another very lightweight admissions process. You say, I want to do this. There's some course requirements, and there's many, many courses to choose from. And then when you graduate, you get your PhD in astronomy or bioengineering or whatever it is with a designated emphasis, a graduate minor in computational science and engineering, which certifies that you're good at this stuff. So let me just give you 2 slides to sort of tell you how broad this is. And I'm going to give you a list of all the departments, and in red, how many faculty have signed up in that department, and in blue, how many courses they teach that are affiliated with this. So you can see that, you know, one of my home departments, EECS, there's 19 faculty and 14 courses in it. There are a lot of things that are related to this. But, you know, there's chemical engineering, chemistry, bioengineering, quite a few. Those all look familiar. But there are a lot of ones which I was pleasantly surprised to see sign up, so including political science. So why are the political scientists interested in this? They have huge databases of how people vote. And they also do large agent-based simulation of political situations. Those are all high-performance computing problems. And so there's just lots and lots of interesting things to learn about. And this is just an invitation about that. So one particular course that I want to tell you about in a little bit more detail is CS267. That is the core course on parallel computing. And we've taught it for many years now. And you can think of this course as a 3-day version of it. This course, 267, is also broadcast all over the place. And we've taught it to students who were enrolled at Santa Cruz and Merced and Davis in the past. And in fact, it's also going to be broadcast by the National Science Foundation and made available to everybody who wants to take it. And let me do this little experiment here. Let's hope I don't break PowerPoint again. So let me go to Google and type in parallel computing course and see what I get. And the top 2 hits are CS267 and this course. So Google is both behind the times and ahead of the time. If I click on this, I get the 1996 version of the course. Now, why would it point to the 1996 version? That's because there's an online textbook which I wrote in raw HTML. I'll never do that again, which is available at that site. And it includes a lot of material that's available for, you know, describing the algorithms. But there's a new version every year as well. And I don't know why Google did this, but if you click on the 2011 version of this boot camp, it should point to the 2010 version. So that last year's is what it really meant. So I don't know why it did that. So and our modest goal, of course, is to have the 2011 one rank 3rd or something like that. Okay, very good. So here's some examples of student projects, because one of the most rewarding things about teaching this course is how excited the students get and how ambitious projects that they do, which they all do posters for. Some of them get publications. Many years ago, there was a startup which made a few $1 billion after a year, and then it sort of crashed in the dot-com boom. That was Inktomy, but yeah, anyway, that's another story. So here's some examples from 2009. So there were projects on content-based image recognition. That's the PARLAB project. Find me all the pictures of the person in this particular picture, no matter where they are in the database. People doing a lot of molecular biology. Molecular dynamics applies to Alzheimer's disease. This is a climate person doing simulations of zooplankton population. How do they evolve as the ocean warms up or cools off? Speech recognition, that's another example from the PARLAB. Gene sequencing, lots of errors in that, again, a biology application. This was an undergraduate application. Their motivation was you're standing around with your cell phone, you're trying to play a game. Hi, Kubi, our next lecturer. You don't have enough bandwidth to play the game, but all your friends are standing around. They have cell phones, they have bandwidth. How do you parallelize a game across all the cell phones of your friends? So that's something that could go viral too. And the last one that was quite interesting was a PhD student at the business school who was looking at the economic implications of parallel computing. How do businesses change the way they implement stuff and become more productive if they can actually parallelize their applications? So these are some examples of projects that people have undertaken, and their posters available. So the CSE designated emphasis has lots of people. If you want to talk to us afterwards, the slides are available there. I'll tell you a little bit about the new courses that we've made, including a new one that's being offered for the first time this semester. Some of the computing resources, we have donations of cloud time. Cloud computing is important. It works well for some applications. You can get startup accounts at NERSC, where you're going to be doing your homework. And I'll tell you a little bit more about LBL and the Supercomputer Center there in a moment. So here's some of the new courses that we've established just in the last few years in order to teach people this stuff. Python for science. This is taught in astronomy. It turns out that many scientists would really just rather program in the highest level language they can and have all the parallelism hidden from them. So this is the beginning of that step, training people in Python. And within the PARLAB, we have projects that take your Python code and try to make it as parallel as possible. You can learn about that on the PARLAB website. So molecular simulation is another new course. This is a very popular one. It's based in MATLAB. But again, the question is, how do you structure it in terms of these basic patterns so that it's easy to parallelize? Earth sciences, again, lots of databases, images of planets, images of stuff on the Earth. How do you analyze it? Optimization codes, again, MATLAB-based. How do you, reduce things to certain patterns that happen over and over again? And one that is going to be offered now for the first time this semester is software engineering for scientific computing. It's basically everything that a non-computer scientist needs to know about databases, about data structures and object-oriented programming and all that kind of stuff that they never learned because they were mechanical engineers or astronomers as undergraduates. And it's meant to be sort of a prerequisite to get the most you can out of a course like this. Okay, let me just tell you a little bit about LBL, which is the very large lab next door, it has a large computing science activity. So thanks to Kathy for these slides. So you're going to be using, for your homework, the 4th largest computer in the United States that's publicly acknowledged, and the 8th largest in the world. It's called Hopper. It's a 1.3 petaflop system, and it has on the order of 150,000 processors on it. You won't get to use all 150,000 to do your homework assignments, but you'll get to use some of them. It has, in fact, you'll have a choice of different machines to run. There's Franklin, which is an older machine. It only has 38,000 cores. Hopper is the big one. There's also Carver, which is just a cluster that your accounts will give you access to. And if you want to do the GPU programming assignments, you'll have access to Dirac, which is a 48-node NVIDIA cluster to do your homework assignments on. But there are lots of other facilities there, and if you're at Berkeley or you have an affiliation with the Department of Energy, these are available for you to use freely. So, and here, in case you haven't seen this before, there's a list updated every 6 months of the 500 fastest computers in the world, sorted by how fast they can do dense linear algebra, how fast they can run Gaussian elimination. And here are the top 10 as of a few months ago. And they're ranked here by this number. That's how many petaflops, 10 to the 15th floating point operations per second they perform dense Gaussian elimination at. Here, the yellow one is the one machine you'll be using. It's just barely over a petaflop. There's lots of interesting data here. For example, how many megawatts these things use, right? You can't just put them anywhere because they use a lot of power. A lot of them use GPUs. That's interesting. That's only come about in the last few years. And they're in many different countries. So there are a lot of people in the world who are deeply interested in this stuff. And there's a website, top500.org, if you want to look at more information about this. So this is, I want to just have one more slide about the intellectual resources that are available at LBL. So there's all sorts of research there in combustion, in climate modeling, the energy, cosmology. And to make all that stuff work, you need a lot of applied mathematics, new algorithms, mathematical models, at the level of linear algebra and parallelizing things to how do I do all the interfaces between flames on one side and not on the other. And there's also a lot of intellectual activity you need in the computer science side and how you map these problems, these new algorithms to machines. All these people are here and collaborating with us, and it's a wonderful environment to do all that in. So in fact, they're also offering a short course, and in fact, it's this week. In this building, down one floor, also broadcast by the National Science Foundation as well as DOE, and it's specialized on a certain number of high-performance tools that are used to solve science problems, Scalapack, PETSI, Hyper. Don't worry if you haven't heard about them. I'm just advertising this because if you get bored with us, you can always go listen to them. And that's also freely available. Unfortunately, their room is already filled up, but they're also broadcasting live just like we are. So you can go look at them. And they're through 16th through the 19th. Okay, and finally, I mentioned that NSF has adopted us. The TerraGrid was the old NSF facility which ran all their supercomputer centers across the country and provided easy access to it. It's just been renamed and refunded and reorganized. It's called EXCEED, which is a funny acronym, Extreme Science and Engineering Discovery Environment. It just started, and they're trying to get more supercomputers, more large databases, instruments, networking easily available to people. But in particular, they're going to do a lot more educational work than they did before. They're going to help people create new curricula. They're going to help form new CSE degree programs, maybe not like the one we have here, but at the undergraduate level, things like that. They're going to broadcast courses like this one and provide computing facilities, so all the people who are taking this course who are offline, not here, are getting accounts on the NSF facilities. And so far, they've adopted 4 courses for nationwide broadcast, including this one, CS267, which I told you about, the DOE workshop I just told you about, and Kurt Koitzer's new undergraduate course, which will be taught again next semester. So, finally, on to the logistics. I'm on schedule. Let me just have the 3 slides of what's going to happen. I'm almost done with my introduction and welcome. Kubi is going to then give you a lecture, with a break in the middle probably, to tell you everything you need to know about parallel architecture and sort of the most basic programming model at the shared memory version, pthreads. Then there'll be lunch, and there's a web page with lots of suggestions, good opportunities around here. Then there'll be a lecture by Tim Mattson of Intel on shared memory programming with OpenMP. Gary Carlton, Berkeley grad from '74, will be talking about prototyping parallel code using a new Intel tool called Intel Advisor. Then another break. Then another one of our Microsoft collaborators will tell you about their new framework, .NET. And then we'll have a break. And then we're going to transition to another large room, the HP Auditorium, across the street in Soda Hall. And at that point, you'll get a little introduction of all the different hands-on sessions, because there's multiple tools that we have hands-on sessions on. You will vote with your feet at that point and decide, do I want to do my homework in OpenMP, MPI, .NET, whatever. I'll say more in the next slide. So that's tomorrow. I'll start off in the morning again, try to wake you up. I'm going to tell you about how parallelism and locality naturally arises in all sorts of simulation problems. Kurt will then tell you and where those 7 dwarfs arose, why they arise naturally from simulations. Then Kurt will do the next level of parallel patterns that I showed you about. Then a break. Then Kathy Yellick will tell you about distributed memory programming in both MPI and UPC, which is another language. Then a lecture on GPU programming. Again, how do you express all these different things in CUDA and OpenCL on GPUs by a former graduate student from Berkeley, Brian, who's now working at NVIDIA. And then, finally, we will go do the hands-on labs. And you'll have, at that point, you'll have decided, do I want to do my homework in .NET, MPI, OpenMP, pthreads, whatever, and you'll go to the right room that we'll have sorted out by then. And then on Wednesday, I'll come back and tell you about the fact that some of this code is so hard to write, it's not fit for human beings. What you do instead is you write a program to write the programs. And it searches over all possible implementations and builds the fastest one. That is one of the tools that we're developing, and it's been done before, but it seems to be the right way to do all sorts of things. We call it auto-tuning. Then there'll be a lecture on a tool for debugging, finding deadlocks. You'll learn about deadlocks in a moment. It's a new kind of bug that you can only get with parallel programs, and it's very helpful to automate that process. Then cloud computing, which is suitable for many but not all applications. Then more tools. How do you find performance bugs? If your program is going much slower than you want, how do you figure out why and fix it? And then finally, we'll close with 4 15-minute lectures on the leading applications in the PARLAB: speech, music, health, and the browser, and how we re-architected them all to use all the tools that you heard about just before. So logistics, coffee, it's outside. The only trouble is you're not allowed to bring it in here, only water and food. I think coffee's food, but what do I know? But if you're the sort of person who insists on your, latte from Pete's, it's down one floor. So you got to go there for fancier stuff. So all these lectures are being webcast live. There is the URL. There's a row of brilliant graduate students in the back who will answer your email when you mail in questions. This is mostly for the remote viewers. So Mike can hold up his hand, Mike Anderson, and Andrew Gearhart, and Aaron Carson, and Razvan Carbonescu, right? So they're the folks who can bug. Sorry, and Nick's sitting on the floor, Nick Knight. So they're the folks who actually will help guide you through all these assignments and answer your questions for the remote viewers. All the lecture materials will get posted to the website. That's my next job after I sit down. For the on-site students, it's a bring your own laptop thing. You'll have these are the languages in which you can do the labs. Tonight, you'll hear more about them in detail and then decide which ones you want to do. We have the wireless access for you to use. There are accounts at NERSC, and we also have accounts on some local machines running the .NET infrastructure that you will use if you choose to learn about that. And all the lab assignments are posted in the class webpage. For the off-site students, it's sort of similar. Please email all your lecture and lab questions to this website and to this email address, and all the teaching assistants will help answer it. You're getting accounts from the NSF on the supercomputer called Ranger at the Texas Advanced Scientific Computing Center, and all we have running there are the OpenMP, pthreads, and MPI versions. So that's what you'll be limited to do. And so let me just tell you a little bit about you. There were 261 people who registered for this course. 112 of you were on site. Perhaps some of you are still sleeping in. And 149 off-site registrants from 45 companies, 61 universities and research organizations. And we didn't ask this year, but last year we said, where are you from? And there were 12 countries. And so who are you? 32 of you said you were software developers or engineers, 24 faculty, 132 graduate students. And so you're a very diverse audience, which makes this course fun to teach. And at that point, let's get started, and it's Kubi's turn. But while Kubi is setting up, are there any questions? Okay.